Let's now consider the growth accounting formula, which is a way to consider how much productivity depends on capital and on technology. Remember, technology, by definition, is anything that raises production at a given level of labor and capital. You have a plant with a certain number of workers, a certain number of equipment. If it can produce more because the workers are more skilled, have better education, or the computers happen to be faster, that represents technology. You can produce more for any given level of labor and capital. Technology is improved for many things, including education and better skills, but there's always invention associated with it. Someone's got a new idea, and maybe that's an idea that comes into the laboratory, but then that idea is brought to the marketplace. It's an innovation in a product and a different way to search, if you like, the internet. And then the idea diffuses. It takes place and affects all different types of products, whether it's Facebook or Twitter. These ideas expand and are diffused throughout, and that's an increase in technology that raises the amount of production at any given level of labor and capital. One thing is to talk about these ideas. Another thing is actually to try to bring them into our analysis in a formal way so that we can determine what happens over time or what's going to happen in the future. And a good way to do that is through this so-called growth accounting formula. It was originally invented by an economist, Robert Solow, many years ago, 1956, 50 years ago. And this idea can be represented in kind of a words equation format that's indicated here on the slide. So it says that the growth rate of real GDP per hour of work, again, that's how fast GDP is rising in real terms compared to the number of hours that people are devoted to producing it. That, of course, is labor productivity. That GDP per hour of work is labor productivity. And so on the left is really the growth rate of labor productivity. And we have argued already that should depend on how much capital workers have to work with and on technology. Those are the factors, those are the ideas or the inputs, if you like, to the growth of labor productivity. What Solow showed is you can calculate this pretty precisely by simply multiplying the growth rate of capital per hour of work. That is how many more machines or factories are available per worker times the number of hours they work, multiplied by 1/3. It's not exactly 1/3, it's about 1/3. We try to get as close as we can. It's an approximate number. But multiply by 1/3, and then you add the growth rate of technology. So this is a direct way to bring in technology into the analysis of what determines the growth rate of productivity. And that's what we're after, both to interpret history, why some economies have higher productivity growth than others, why productivity growth is a relatively recent phenomenon. It didn't occur for many centuries until the last few centuries, and what might happen in the future. So here's how it goes. I want to actually explain how this formula works using basic macroeconomic analysis. So the starting place is what we'll call the productivity curve. Productivity curve looks a lot like a production function, has a lot to do with the production function, but it's not quite a production function because, as you can see on the horizontal axis, we've taken capital and divided by labor input, symbolically K over L. And on the vertical axis, we divided product, Y, and divided by labor input, symbolically Y over L. Vertical axis has another name, labor productivity, and the horizontal axis is simply just the amount of capital each worker has to work with over time. It has diminishing returns, just like a regular production function, but the axes are somewhat different. You can think of this symbolically, if you like, with this little format here, some symbols that might help, not necessary, but might help understand. So the production function we can think of algebraically as a statement that real GDP Y depends on technology, T, on labor raised to the 0.7 power and capital raised to the 0.3 power. It's just an example of a production function, which economists have found pretty useful to represent production over time in an economy like the US. If you take that production function and divide both sides by L, just as in the productivity curve. Remember, the vertical axis had Y over L and the horizontal axis had K over L. So if you take this and divide both sides by L, you'll see on the left-hand side you have labor productivity, And on the right-hand side, because you're dividing L to the 0.7 by L, you'll have L to the 0.3 in the denominator. So you have T times K over L raised to the 0.3 power. And so you have productivity, Y over L, depending on capital per unit of labor, K over L. And you can see with that 0.3 exponent, it has this diminishing returns. And that's what we just showed in this diagram. So it's another way to think about it. Now, with that way of thinking about it, we can now try to derive the growth accounting formula. So let's start with a picture of what happens when there's more technology. With more technology, a given amount of capital per worker, per labor input, is going to result in more productivity, more output per labor input. That's what's demonstrated here. You can focus at point A, the amount of capital per labor input. More technology will enable you to produce more for each worker for a given level of capital. It raises up the amount of productivity. Now that's what happens. We know that happens with technology. The question is, how can we use this shift of the curve versus the curve itself to divvy up, as Solow did in the growth accounting formula, between capital per labor versus technology? Let's think of it in terms of an example. Suppose this is productivity growth in year 1 and in year 2. Same axes as before, productivity on the vertical axis, capital per unit of labor on the horizontal axis. So year 1 has lower productivity than year 2. There's productivity growth from year 1 to year 2. There's also more capital in year 2 than in year 1. So there's been a growth of capital per labor input. So the job that the growth accounting formula gets done is to divvy up how much of that increase in productivity is due to capital versus technology. And here's how you do it. You just superimpose on that picture of the two different levels of productivity, the production function, or the productivity curve more precisely. And I've drawn it so the productivity curve cuts through year 1 and it cuts through year 2. And you can see now that what we've observed in the increase in productivity is two things going on. You basically have the shift upward in the curve, okay, that accounts for some of the increase in productivity. And then you have a movement along the curve, and that's the rest of the increase in productivity. The total amount of increase in productivity between year 1 and year 2 is that amount. And we've now argued that some of it has to do with the shift up of the curve, just to repeat, and some of it has to do with the movement along the curve, the new curve. And what the growth accounting formula does is find a way to divvy that up so that you can use data to analyze which is which in any given period of time. It's quite remarkable. So it's the shift versus movement along again, in this case, the productivity curve. So let's see how you do this algebraically. And to do that, I want to continue to focus on this curve. I'm going to try to put it on the screen down at the lower so you can look at that as we look at some of the algebra that goes along with this. So first of all, we know that we've divvied up, just as I've indicated with the picture, the increase in productivity into the shift and the movement along the curve. So on the left here, we see C minus A, and that's the total increase in productivity from year 1 to year 2, C minus A, that's in the picture below. We're dividing by A because we want to look at a growth rate of productivity. The growth accounting formula has to do with the growth rate of productivity. So C minus A is the change in labor productivity. If you divide by A, the productivity at the beginning, that's a percentage change in productivity. It's stated as a decimal. Okay, so that's your productivity growth. And that's divided into these two terms. One is C minus B, and you can see that in the diagram over here. That's the amount due to movement along the curve, and the B minus A, that's the shift of the curve. And both of these we've divided through by A so that they're percentage or growth rates. C minus B over A is the percentage change that's due to movement along the curve. B minus A over A, the percentage change that's due to the shift of the curve. Okay, so that's all there is to it. Now let's sort of put in some symbols so we can make this go to work with the data. The growth rate of productivity, to repeat, is on the left. The effect of more capital per unit of labor is the first term on the right. And the remaining term is this growth rate of technology. That's what we're calling the shift of the productivity curve. Okay, so symbolically, let's look at symbolically what the effect of more capital per unit of labor looks like, that term C minus B over A. Well, here's what it is. In the numerator, we're looking at the change in capital per unit of labor. That's the movement in this curve along the horizontal axis. That's the change from year 1 to year 2 in capital per unit of labor. We've multiplied that by R, which is the slope of the productivity curve at that point. So we multiplied that distance by that slope, and of course that should give us the distance on the vertical axis. Okay, so you take the change on the horizontal axis, multiply by the slope, and you get the change on the vertical axis. So it's just another way to represent C minus B. We've divided by Y over L, that's productivity, but that's just another way to represent the number A. And so we've just rewritten C minus B divided by A with this delta K over L, the change in K over L times R divided by Y over L. Pretty straightforward. Next, let's just simply divide both sides of that by K over L, capital per unit of labor. That's what's done in the second equality here, second term. And now let's just associate terms and see what we have. So we've taken the K over L, one of the K over L's, and left it in the denominator. The other K over L, we've noted that it can be divided into by the Y over L, so the K over L in the numerator divided by Y over L. The L's cancel when you have K over Y. We're going to think about that for a minute. So we've now changed this into R times K over Y. Now think about what we have. We have the percentage change now in capital over labor. That is the change in K over L divided by K over L. That's that percentage change, stated in decimals, of course, just to be sure. And now we're multiplying by the slope of the productivity curve times K over L. Now finally, to sort of wrap this up and see what we get, if capital is paid its marginal return, if you like, the extra output that is obtained by increasing capital, then that should be R, because R is the marginal product of capital. It's what happens if we increase capital a little bit, how much output you get. That's what we mean by the slope of the productivity curve. A little bit more capital gives you a little bit more output. That's the marginal product of capital. We've argued in microeconomics that the rental rate or the implicit rental rate on capital, the return to capital, should be roughly equal to that marginal product. And so that marginal product can represent the return on capital, how much capital is paid, if you like. You multiply that by the amount of capital, and you get the total payments to capital, how much capital is earned in the economy. Divide that by a total Y, a total GDP or total income in the economy, and you get the fraction of income that's paid to capital. It turns out that fraction is about a third, and that's basically how it finishes. We now have a measure of the growth rate of capital per unit of labor. That's multiplied by nothing else than 1/3, which is about the amount that capital gets paid relative to total income in the economy. So that's that term in the Solow growth accounting formula that Solow discovered through this type of reasoning. Of course, the last term on the right is the growth rate of technology. And so that's it. That's the rationale. Slopes versus movements alongs, recognizing the marginal product of capital is in the productivity curve. Now let's just finish by thinking about how this gets applied to history or to the future. If you think about history, you think you'll have data, economists have data on productivity growth. That's on the left. So real growth rate of real GDP you can obtain from government statistical agencies as you can the number of hours of work in the economy. So that you get your measure of productivity pretty straightforward. You also can get a measure of capital per hour of a work by looking how much capital there is and dividing it by labor input, L, and you consider the growth rate of that on the right. You can multiply that by 1/3. And what's left over from that is this growth rate of technology. So for example, from 1950 to 1973, productivity growth averaged 2.3% a year. Growth rate of capital per hour of work averaged about 3.3% a year. So you multiply that 3.3 by 1/3, subtract it from 2.3, and you get 1.2. And that's our estimate of the contribution of the growth rate of technology to productivity. You could now consider what might have led to a decline in productivity in the 1970s. Was it capital? Was it technology? Or what occurred to a resurgence of productivity in the 90s? A very important application of this was what happened in the Soviet Union, because economists using this approach noted that much of the growth in the Soviet Union had to do with just capital, very little technology impact. And of course, capital has diminishing returns, and so with very little to do with technology, the Soviet Union economy slowed down, was unable to compete, and so it basically was one of the reasons why the Soviet Union eventually ended. And then finally, that's history. Finally, there's the future. You can use the same growth accounting formula to look at productivity growth, economic growth in the future, and this is another example of that. So from 2013 to 2023, the Congressional Budget Office, for example, has an estimate that productivity growth is 1.6% a year. That's divided into 1/3 times 3. 3 is the growth rate of capital per unit of work, and 0.6 is this technological input. Now, what would happen if you had more capital, if somehow more investment occurred and the capital grew more rapidly, say by 6% by 3%? Well, you can calculate right away. You can do that for homework. Or if there was less capital, the 3 changed to a 0, right away you can see that's going to have a big reduction in productivity growth. You could also see what you could do to get technological growth more. Well, that has to do with education, the impact of regulation on the economy, the amount of skills workers have, the incentive for more skills to be obtained. And so using this framework, you can actually get quantitative estimates of how much growth might improve with more capital. That's a public policy issue. Should we encourage more investment? Or how much it will increase if you stimulate more inventions and innovations. That's how it works in the future. We've seen how it works in the past. And perhaps most importantly, we've seen how it was derived and get a better understanding of how it really helps us make these decisions. Thank you.